Good evening. It's wonderful to be here, and I want to thank all the organizations involved for organizing this event. So this is a popular lecture. It's not aimed primarily at physicists. Let me ask you, who is not a physicist in this audience? Wonderful, the lecture is really for you. So this lecture is also a little bit special because it's not just a popular science lecture. We also want to celebrate German-US relationship, and we want to honor the special role of Heidelberg and the University of Heidelberg. So I decided to actually cut down a little bit on the science, have a few remarks about my career growing up in Heidelberg and such. And then I want to give you more the basic idea, what is my research area about, why was a Nobel Prize given for that, and then I only talk the last 5 minutes about what we are currently doing in research. But I hope this is more meeting also your interest to not get so many details, but maybe walk out with a feel that, yeah, there is something cool and exciting going on in physics. So I grew up in Heidelberg, and I went to high school in Heidelberg, to the Bunsen-Gymnasium, which is actually very close to the university. And after my high school diploma or abitur, there was a high school, you can say, commencement celebration in Alta Aula of the university. And I think this was the first scientific talk I ever gave, and it's actually funny, I chose as a topic Einstein's theory of relativity for non-physicists. I think this was the worst talk I ever gave because I wanted to really explain it, and I realized there is only so much you can explain in 30 minutes or so, and sometimes I would now say the more you want to cover, the less you uncover. So I hope I've learned a little bit in the last 30 years, and I will uncover something for you today. So I remember when I started my studies in physics at the University of Heidelberg, and I have to share this picture because this is something I've never forgotten. This is the old physics lecture hall, and it's in this old traditional building in the Institute for Physics, and who actually of you has been in Heidelberg? Okay, so you may have an idea, at least half of you, of the river, and then there is the Philosophenweg. And the old Institute of Physics is right there at the Philosophenweg, and it's 100 years old. Physics now in the last 10 or 20 years has moved into Neuenheimer Feld, into a new area. But this old physics lecture hall, this is what I experienced as a student. And look how steep it is, twice as steep as here. And I remember when I walked in and looked down, it looked like the dungeon of physicists, where the physics professor, Otto Huxell, an old person, he had a bow tie and he was really celebrating physics. It was exciting, and this was my first physics lecture. And this is still in this lecture, shows this picture of the lecture. I went to Munich for PhD, so this shows a handsome young man, me, at the beginning of my PhD. And it was successful and followed the German tradition. We celebrated the PhD with a special mortarboard. And my mortarboard, what it shows here, is actually a model of the molecule I studied. Yellow are the electrons, red are the protons, blue are the neutrons. Do you see what kind of molecule? This is, one proton is hydrogen, 2 protons is helium, helium hydride, a special molecule, and 2 electrons symbolized by the yellow pink protons. So I went to Munich, got my diploma and PhD there, but then I came back to Heidelberg as a researcher, and I worked in physical chemistry. You see here 2 colors of laser beams intersecting a flame. So understand what's going on in combustion in a flame or even in a diesel engine by using laser technology. So this was sort of interesting. You work on diesel engine, you work on cleaner combustion, and it's something where you connect with the real world, with applications, with the demands of society, and you can tell your family, I use laser light for cleaner environment, and you say, that's great. Well, I made a big change in 1990. I made a big change to go from my native Germany to the United States, to go from the study of very hot flames to the study of the coldest matter of the universe. And I went from applied research, where it is so easy to tell, I don't know, administrators, politicians, lay people, what I'm doing. You know, laser light for cleaner combustion. I went to basic research. And now I'm facing the challenge to tell you that I'm so excited about a tiny little bit of gas because it is so cold. And that's what I try to tell you today. So when I came to MIT, I started the study of very, very cold gases, very, very cold materials. And what I managed to do is to create the coldest matter in the universe. And this is what I want to tell you. But maybe I should first make sure you make a connection. At ordinary temperatures, do you know how fast molecules are? How fast is the air molecule moving around here? Is it speed of car, speed of bullet, speed of a rocket, speed of light? It's okay. I sometimes say when I give a lecture, there's only one thing to remember for the rest of your life, I'm happy. And if it's just that, I've maybe done a good job. The molecules in air move at the speed of a jet airplane. And you will never forget it because I'm explaining it to you. The jet airplanes move at around the speed of sound because if you go a little bit faster and break through the sound barrier, it has environmental and other consequences. But airplanes, jet airplanes, stay close to the speed of sound. I can only talk to you because my voice travels to your ear at the speed of sound. And the air is really transmitting my voice at a speed which is given by the speed of the molecules themselves. So speed of sound, speed of molecules in air, and jet airplane are all connected. So this is ordinary form. This is how ordinary matter behaves. But I will tell you that we are able to bring molecules from jet airplanes down to a standstill. If I would release cold atoms into this room, by the end of my lecture, they would not reach the end of the room. They really slow down to a comma. Anyway, that's pretty remarkable, pretty dramatic, pretty cool, but why would you like to have cold atoms? What's the purpose of getting colder and colder? One thing, of course, is it's a challenge, and in physics we always make progress when we take things to the extreme, sometimes immediately and sometimes in the long run. But there was a clear motivation why people were working on methods to get colder and colder atoms and molecules. And the reason is the following. The timekeeping of the world, atomic clocks, are based on atoms. I mean, for global communication and navigation, we need very, very precise clocks. And we're not fabricating clocks like wristwatches because they are all different. We are still fabricating them, but they are not defining the time. The time is really defined by the ticking inside an atom. Because atoms are identical everywhere, so there is no problem about, different adjustments. Each atom has exactly gives the same time. But that means you have to observe atoms. You have to observe the ticking. And actually the ticking inside an atom is the motion of an electron or the electron spin. So now, remember, but normal atoms and molecules move at the speed of a jet airplane. And this is why people constructed atomic clocks like this. Cesium atoms move at 100 meters per second through this tube. And you just have to, very quickly read the time of the atoms because it takes 10 milliseconds. You have 10 thousandths of a second to read the time. Then the atoms hit the end of the tube. You would say that's crude, but these were the most precise atomic clocks, and they gave rise to global positioning system and other things. But now, when we can bring atoms to a standstill, we have reduced the velocity of the atoms by factors of 100 and 1,000 and more, and in more recent frequency standards, the velocity of the atoms, they are 1,000 times slower, and therefore the precision of the timekeeping is 1,000 times more accurate. So it was ultimately the accuracy of physical measurements, of scientific measurements, but also the practical application of precise atomic standards which motivated physicists to bring atoms to lower and lower velocity from the speed of a jet airplane to almost a standstill. But in terms of fundamental science, that's cool, but not particularly novel, because it means everything is just in slow motion. A gas which is colder is just a gas where everything happens slower. Now, if we would cool down the temperature in this room by a factor of 10,000, well, we would all be freezing, but never mind, then it would take 100 times longer for my voice to reach you. And in the extreme case, I would say something, and because the gas is so cold, the speed of sound would be such that it would take you a minute until you hear what I'm saying. But this is just, everything is slowing down. But now something happens. If you go to lower and lower velocity, it's not just slowing down. There is a sudden phase transition where the whole physical system of atoms changes its behavior. And this is depicted here. The atoms are not just moving more slowly, and this was the new form of matter which Bose and Einstein predicted 70 years ago before we realized it, that when it gets colder and colder, atoms are starting to no longer move slowly relative to each other, but march in lockstep. And this is some remarkable new form of matter. I like this cartoon, it really captures a lot of the physics, but what it doesn't capture is that it's a quantum-mechanical phenomenon related to the wave nature. So one should rather say that those atoms lose their identity as being atoms and they just behave as one wave. I know I put superfluidity in the title, let me just make a remark here. You have probably heard about superconductivity, possibilities of sending electrical power through wires without any losses, because the electrons literally march in lockstep. So you can really understand that in the following way. Assume there is a crowd of people and everybody is bumping into each other. This is what electrons and atoms do normally. But if you make everybody march in lockstep, you can make people move, many people move without friction. And this is the idea of superfluidity and superconductivity. And what we realized here with Bose-Einstein condensation, and this was a prediction, at very low temperature, a gas will really show this superfluid behavior, which I translate here, behaving as one big wave or marching in lockstep. And I want to show you a little bit later in my lecture how we showed directly that atoms march in lockstep. But let me first give you also another example. I said there is a gas at low temperature is not just slowing down, there is a phase transition to a fundamentally new form of matter. Let me give you the analogy with light. You know what ordinary light is, and you know how profoundly different the laser is. And the laser light is coherent. All the photons march in lockstep. The electric field is one big wave, whereas in ordinary light, photons go in all directions randomly. So all the differences you can emphasize between ordinary light and laser light can also be applied now to atoms and characterize what is going on in a normal gas at higher temperature and to this new form of matter where atoms march in lockstep. So if you ask me to explain in one sentence what discovery I've made, I would say I created atoms with the properties of laser light. Or I did for atoms what the laser is for light. An organized new form of matter with new properties. I could give you a whole lecture how we cool down to those low temperatures and how we create temperatures which are a billion times colder than interstellar space. But, well, I rather talk about other things, and I just want to show you what happens in the laboratory, that you get a feel how the research is done, And then I want to show you what are we doing with these cold atoms. And how we exactly cool them, you can ask me at the end of the lecture, or just trust me. We make atoms really cold. So what we have here is a laboratory, it's a table, and the table has a vacuum chamber. But then it has, and here you see the window of the vacuum chamber. But it has lots and lots of cables and optics, because we need a lot of bells and whistles to control all the different stages of our experiment. But the most important part are the studies. This is fundamental research done on campus at a university, and the people who design, build, and operate the equipment are undergraduate students and graduate students, and sometimes postdocs. Here you sort of see a close-up. You see a vacuum chamber here. This is about 1 foot. Here is a window, and it is right behind the window that we form matter at extremely low temperatures. And you recognize, yeah, we need big magnetic fields, so we need cables, water cooling. So it's a lot of experimental effort, but at the end of the day, the physics we are doing can actually be easily described. We need laser light for all different purposes, and I will mention some of them. But here I just want to catch the atmosphere. When you walk into one of our labs, you can really see light which goes back and forth between mirrors and optics. And sometimes we use different colors. Yellow is the natural light of sodium, red is the natural light of lithium, and here we even use some green light for some special purposes. And here you see laser cooling in action. So I'm not explaining you how it works, but I'm telling you we have some hot sodium vapor, which is like the vapor in the yellow street lights. But then by carefully tuning our laser light, we are zapping all the energy away from the atoms, and then we have a fuzzy cloud of atoms. You can just look at it with the naked eye. It just looks like a little yellow cloud which is levitating, hovering in this vacuum chamber. But those atoms are 1,000 times colder than interstellar space and about 1,000,000 times colder than room temperature using the Kelvin scale. So anyway, I haven't really told you how we cool it, but I want to really give you an impression that you can understand what are the experiments we are doing. So using all the tricks which the field has developed, we can create millions of atoms at nanokelvin temperature, extremely close to absolute zero. Those atoms are so cold, we have to isolate them from the room temperature environment. And there is no box, no material confinement which would do that, because we can only cool the atoms with our methods. We could not cool a container. So what we use is we use an invisible, immaterial container made out of electromagnetic fields. And then we have ultra-high vacuum around it. So the idea is we have a vacuum chamber this size. There's ultra-high vacuum, which is the best thermos. And then in the middle of the chamber, isolated by this extreme vacuum, we are holding on with electric and magnetic field to a cloud of atoms. And this cloud of atoms is a million or several million atoms at very, very low temperature. So the size of the atoms is a fraction of a millimeter, maybe the dimension of the human hair, but with a few lenses you can easily see what's going on. So how do we figure out what is going on there? We cannot touch the atoms, they are so cold, but we can look at them with laser light. So one technique is, which is actually very powerful, is we switch off the electric and magnetic field. Now there is nothing anymore which is confining, which is holding on to the atoms, and the atoms will just fall down due to gravity, but they will also expand due to the residual thermal motion. So in other words, the cloud expands, and now we can illuminate the cloud with laser light. The cloud is scattering light, it casts a shadow, and what we observe here is the shadow of the cloud using a digital camera. So this is actually how we measure temperature. This is how we know that we have reached nanokelvin temperatures. Because imagine we have a small cloud initially held by electromagnetic field, and then it expands. So that's how we did. And if you look at the size of the cloud after a certain time, we've actually measured the velocity of expansion. And now this is the most complicated formula I want to show you today. You put this velocity into the formula for kinetic energy. You know the kinetic energy, but the kinetic energy is just a measure for the absolute temperature. So it's the velocity of the atoms which we directly measure. And I said it's really slow, much slower than the speed of a jet airplane. And this is how we determine the kinetic energy and the temperature. So what I want to show you now is a series of those pictures. It was actually the way how we observed for the first time this new form of matter called the Bose-Einstein condensate, which Bose and Einstein predicted. And I just want you to see the following. So we have a bunch of atoms, we cool them down, we switch off the electric and magnetic field, which forms the box, and then the cloud expands. Those atoms are pumped out of our chamber, they've done their job. But now 10 seconds later, we take another bunch of atoms, and this time we tune our cooling methods to a little bit lower temperature. And then we take the next picture. What's the difference between the first and the next picture? The cloud is a little bit smaller because at lower temperature, the atoms have a smaller velocity and therefore will expand less. So what I want to show you now is what happens. We are at more than a million times colder than interstellar space, and now we are getting close to Bose-Einstein condensation. So what do you observe? You observe a cloud, and on every subsequent realization, the cloud is, when the animation starts, the cloud should get smaller and smaller. Yeah, now you see how the cloud shrinks, it's getting smaller. But it's not just getting smaller, suddenly something happens. Something forms inside. It looks like a cherry with a pit. And I can play it again for you. And what forms inside, these are actually the blue guys which march in lockstep. This is the Bose-Einstein condensate. It suddenly forms, it's a phase transition, so we have reached the temperature where this phase transition happens, which is as sudden when you cool water to the freezing point and suddenly ice forms. So this is like suddenly ice forms, a new form of matter. But the other thing, so there are two things which you immediately see here. These atoms, who hardly expand at all, so they must be really cold, and yes, indeed, they are really cold. And the second thing you realize is the shape is elliptical, but initially the shadow was round. So what was going on? Well, I didn't tell you that our magnetic box, which we used there, is actually elliptical, but for a normal cloud where everything is in random motion, particles move in all directions with equal probability. If I let the atoms expand from an elliptical container, they expand in all directions and the shadow is round. But these blue guys, they are more like a wave. And when they are in an elliptical container, they expand in a wave-like pattern which looks elliptical. So this was already an immediate evidence that what has formed has different properties, is a new phase of matter. Okay, so I want to introduce this Bose-Einstein condensate also to you a little bit like a new material. I try to at least give you some pictures and background how we made it. I've shown to you that it's very cold, but now I want to focus on two remarkable properties which have actually created this enormous interest in this form of matter. One is it's made of waves. It really, what goes on here is, yes, these are atoms, these are particles, but they behave like quantum mechanical waves, and we need the wave description, the formalism of quantum mechanics to understand them. And I also want to show you that they are superfluid. So how do you prove that atoms march in lockstep, or that they are one single wave, that they are coherent? Well, we usually show in physics that something has wave-like properties by what we call interference. So let me explain that. If I take a bag of paint, throw it against the wall, then I get a red spot. If I take a second paintball and the two red spots overlap, I find here the simple equation, red paint and red paint gives darker red paint. But now, and paint in this context doesn't have the properties of waves. But if I now use a red laser beam and I overlap two red laser beams, I find something very different. I find an interference pattern of high and low intensity alternating, and what I find here is the equation, let me now focus on maybe the dark fringe, that light and light can give darkness because the positive electric field of the light and negative electric field of the light can add up to 0. You also see that when you go to a lake and throw two stones in it, there is motion. But motion and motion can add up to a standstill because positive and negative velocity can add up to 0. And this is shown here. If you have two stones, they form a circular traveling wave, form a standing wave here. And here you have some nodes of the standing wave where motion and motion give standstill. So now the question is, if we take two Bose-Einstein condensates, it's a false color picture. We have one Bose-Einstein condensate, but then we took a laser knife, a green laser beam, and we were cutting the Bose-Einstein condensate into two pieces. So now the question is, if you have two Bose-Einstein condensates and we switch off all the magnetic and electric fields, they fall down, but because the atoms repel each other, they also penetrate into each other. And now we take a shadow picture with a digital camera. And will these atomic clouds now behave like red paint, or will they behave like laser light? And this is what we saw. So what you see here is the interference pattern between two Bose-Einstein condensates, where there is, we cannot use a lot of light, so the light is a little bit noisy, but this is sort of light. And now where you see darkness, there is a shadow cast by the atoms. So where we have darkness, there are atoms, but in between the dark lines, the light goes through, therefore there are no atoms. So this dramatically showed that the atoms behave in full analogy to laser light. And if I look here at this region where the light goes through, there are no atoms, what that means is atoms and atoms can add up to nothing, exactly in the same way as light and light can add up to darkness. It's just the physics of waves, and here what we have is the interference of quantum mechanical waves. So when I received the Nobel Prize in 2001, and the Nobel Committee actually highlighted two accomplishments. One was the techniques and the techniques to produce Bose-Einstein condensates and the observation which I'm showing you. And the second thing which was highlighted was this observation of the wave nature of the fact that the atoms are laser-like. So when you go to Stockholm and receive the Nobel Prize, it's of course a fantastic event. It's a whole week of celebration. It's a perfect party and the perfect, the suites are really perfectionized over the years, how to do honor to the scientists. You're in the nicest hotel in town, you have a driver with a limousine just for you to drive you around. You're invited by the king and queen to have dinner. And your Nobel diploma is a piece of art. And my Nobel diploma shows my research. It shows the Bose-Einstein condensate, which is cut by a laser beam into two Bose-Einstein condensates. And now these atoms are atoms, little bullets, but they are also behaving like waves. And this here is the artist's rendition of the interference pattern I showed you on the previous slide. Okay, so this demonstrated that the atoms behave like waves, but we also wanted to show that we can now we cannot just expand Bose-Einstein condensate, observe this interference, we can also put motion into it. We can move atoms around, and they move around in a superfluid way. So superfluidity really means eventually that there is no viscosity, but we showed that later. But what we could show first was the fundamental difference between superfluid behavior and normal behavior. And I want to illustrate that here. If you take a bucket of water and rotate it, well, after a while, the water rotates with the bucket. And there is one effect of the rotation you observe, and this is due to centrifugal forces. There is this meniscus, but otherwise the water just rigidly rotates with the bucket. If you fill a bucket with a superfluid helium, or at least in the thought experiment, a Bose-Einstein condensate, it cannot, it must not rotate like water. It will form quantum vortices. It will show a dramatically different behavior. And this is usually in the field of superfluidity, quantum gases and such, this is regarded as the smoking gun, that this is a superfluid. So let me explain why a superfluid cannot move around, cannot move in circles as a normal fluid, as a bucket of water. And this is related to the wave nature. And the two things I just want you to know is every atom, every particle, actually every object, you and I, we have a wave nature. And there is a wavelength, and the wavelengths of the waves, the wave pattern is more extended. The wavelength is the longer, the smaller the velocity is, or the colder the particle is. By the way, it's also inversely proportional to the mass. So if you calculate what your wavelength is and you put in your mass, you find that it is so small that it never matters for anything. So this is why you should probably never regard yourself as a wave. You are kind of a particle in that sense, and you never show wave properties. But what I want to just keep the thought, atoms have wave character, because we are talking about small velocities, everything is sort of on a scale where we can observe it. And finally, the wavelengths gets shorter and shorter when the particles move faster. So what does it mean now? If we want a liquid in a bucket to move in a circle, rigid rotation, when the water rigidly rotates with a bucket, means that the velocity linearly increases. It doesn't move in the center, and then the velocity increases linearly according to distillation. This is how water rotates. But a superfluid is a wave, and the wave has to close in itself. This is what quantum mechanics tells us. We need an integer number of wavelengths per circumference. So therefore, the superfluid can only rotate in steps. It is not rotating at all. Then it rotates with a velocity which is 1 wavelength per circumference, then it jumps to 2, then it jumps to 3. So what I'm telling you is the wave nature which forces velocity to be discrete, 1 wavelength per circumference, 2 wavelengths per circumference, would now mean that there are singularities where the velocity suddenly jumps to another value. This is the nature of waves. Waves cannot rotate in an arbitrary way like water can move around. They have to follow their wave nature. Okay, so what I try to explain to you here is by the very wave nature of particles, the atoms cannot move in a continuous velocity pattern. There must be jumps, there must be discontinuities. Well, if you look at it more carefully, you realize that there is a more favorable way how the atoms can rotate, and this is shown here. Instead of having sort of singularities, discontinuities of the velocity in concentric rings, in concentric cylinders, it's slightly more favorable energetically if these discontinuities come in lines. So the wave nature of particles now means that the rotating superfluid has, looks like Swiss cheese, where each of those points is a little whirlpool. It actually looks like a tornado. You're familiar with tornadoes on a big scale. We are all familiar with tornadoes on a smaller scale. And what we see here are now tornadoes in the quantum world, intimately related to the wave nature of particles. So what we did is, all we had to do is to show that, well, there were a lot of experimental challenges to do it, but we had a Bose-Einstein condensate, and you know already about the shadow picture, but now we use laser beams and rotated them around it. It's a little bit like a ping pong ball. You take a feather, and then you move the feather around the ping pong ball, and the ping pong ball starts spinning, starts rotation. And then we switched off everything. We use our normal technique. The cloud expands. We take a shadow picture, and this is how the shadow picture looks like. You would never expect that from normal physics, but this is the property of the superfluids. So maybe you can go home now and can tell, I don't know, your children or your special other, this guy really showed us weird stuff. He was talking about gases, but he showed us gases which look like a zebra, and now he shows us gases which look like Swiss cheese. So this is really what happens in the quantum world, and this shows that we have a new form of matter which behaves like waves and is also superfluid. So this is research we did in the foundational period of the field, slightly before or after the Nobel Prize was given in 2001. But since then, we have firmly established those cold atoms as special new materials with special properties. So I've mentioned already the special properties of that. But in our current research, we are now really regarding the atoms as Lego pieces. If you bring atoms to a standstill, you can now move them around with laser beams and magnetic fields, and you can assemble them in new ways. And if I had more time, I could tell you about many of the things we have done, but I only want to give you one example at the end. But let me first connect it to the diagram I've shown you before. So we have these very, very cold atoms, and I showed you the basic properties of that. How it expands and is really cold. You remember the ellipse. When we cut it into two pieces, it looks like a zebra. When we rotate it, it looks like Swiss cheese. But there is many more things we can do. We can just send laser beams on it, use radio frequency and microwave fields, and there is an endless number of possibilities and opportunities how we can modify the behavior of this gas. We can turn it into a metal, we can turn it into an insulator. There's so many possible ways, but all is done in the following way. We have this vacuum chamber, and we are just sending laser beams and electromagnetic waves and magnetic fields into it, and this is how we shape these atomic Lego pieces and assemble them in novel ways. So at the very end, I want to mention something special we've done last year. We've used these cold atoms in our cold Lego pieces to create a new form of matter. And since the time is advanced, I will not try to explain it to you into detail, but at least I want you to give you an idea that you walk away with, wow, yeah, physics is really moving on in new directions, and it's really a never-ending story of discoveries. So I want to talk about a new form of matter which is called supersolid, but maybe to the non-scientist I want to first tease you. It's actually a form of matter which is a gas, a liquid, and a solid all at the same time. And especially if I talk to young students, they start giggling, what my school teacher tells me is wrong. They tell me it's either one or that, and now they hear that it can be a liquid, solid, and gas at the same time. But let me just demystify it. This is maybe not so special, because we have 3 dimensions in space, and I could easily think of some substance which is sort of moves around like a gas in one direction, like a liquid in the other one, and in the third one it behaves like a solid. So to combine different properties in different dimensions of space is maybe not so special. But what was really special and what was a challenge is, can something be solid and superfluid at the same time? And yeah, when we eventually, me and another group in Switzerland managed to do that, there were a little bit of, wild reports in the, scientific literature, the wild new super solid, and, this was a way to try to capture it. But let me maybe just tell you what is special about it, and then I can take your questions. So, why this was special is the following. In a solid, think about a crystal. Each atom is localized in a periodic array. And therefore, also the atoms are indistinguishable by, each sodium atom is the same. Those atoms are distinguishable, and I indicated here by colors, because they have a different position. You can say this atom is bound in the crystal, and if I come back later, it's the same atom. It's distinguishable from its neighbors just by its position. But, so atoms are localized in a solid, usually. But in a superfluid, remember, it's particles behaving like a wave marching in lockstep. So this is more a cartoon picture of how you should think about a Bose-Einstein condensate or superfluid. So it seems those two things are mutually exclusive. However, there was a way to combine it, and this is the following way. A solid does not require to have particles sort of separated. The defining feature of a solid is that it has shape, that it has form. Gas has no form, it fills any container. A liquid fills any container. But a solid has a shape or form. And I'm not telling you the story because it's a little too complicated, but we used the Bose-Einstein condensate, sent a few laser beams at it, and then we saw that we had created a super solid. So let me have two slides as a summary. So in our current research, we use cold atoms and Lego pieces to obtain a deeper understanding for materials. We want to try out with our Lego pieces what are the new opportunities in nature to create new materials. I want to be perfectly honest, if we create something at those low temperatures in our high vacuum chamber, it will not have an immediate practical use. But once we show that something is possible in nature, in the future, in 10 or 20 years, material designers can take those concepts and try to implement them in materials which then hopefully have practical applications. Now, I also want to mention is that the work we are doing is using atoms, quantum objects, is really related to something which is much bigger than our research. It's quantum technology. There are national programs in Europe. We soon will have in the United States a national quantum initiative, because quantum science is also now ready to connect basic research with applications. And you may hear and read in the newspaper buzzwords about quantum technology, quantum cryptography, quantum computer, and what I gave you is intrinsically related to those challenges. So I've talked today mainly about superfluids and a little bit about super solids, but what is currently of interest in my laboratory are also other materials. We want to look at different magnetic forms. We want to solve some mysteries about magnetic properties of nature, and we also want to look at topological properties, which is a special twist. So again, once you have answered one question in science, you can now ask in a meaningful way 2 new questions, and these are questions which we are currently asking. So with that, I thank you for your attention.